Looks like we're live. Hello everyone and welcome to another recreational programming session. So let's make a little bit of an announcement and officially start the stream as usual, as we usually do. I just need to bring my Discord server. And let me do right circle live on Twitch. And what are we doing today on twitch.television? Let me see. Today we are exploring a very interesting technique in Jai specifically, not only in Jai, called relative pointers, right? So if you've been following the development of Jai, you probably heard about these things. And I would like today explore them a little bit closer. So that's what we're going to be doing today. Hello everyone, welcome. So somebody's just honking outside. So to be fair, I've been using a form of relative pointers for quite some time already in my C++ programs, primarily C, right, because I don't really program in C++ very often, unless it's absolutely necessary. So let me go and create maybe a folder where we're going to do all of our experimentations, right? So relative pointers, right? So, and let me open like a C program of some sort. All right. So quite often, instead of using pointers, I would use indices to a particular array, right? So let's imagine that I want to build a binary tree. So I'm going to define a node, right? And a node is going to contain some sort of a text, right? So it's going to contain some sort of a text. Let's say it's going to be 32 characters, right? It's not going to be very big text, some sort of a label. And it is going to store a pointer to the left subtree and the right subtree. And that definition is not going to work, right? Because we're referring to node before it was actually properly defined, because it's C. So what we have to do instead, we actually have to move this thing like that, right? And then define something like this, right? So we predefine the struct, and only then we'll be able to, to forward refer to that. I don't remember. So we have to forward declare this entire thing. Right, so this is how you can define a binary tree, but quite often what I would do, I would actually have some sort of a pool of the nodes, right? So node pool, and I'm going to have a certain capacity of that node pool, right? So let's actually define something like this. And let's say that we're going to have 1024 of such things. And instead of referring to left and right as an absolute pointer in the memory, I would use some sort of an index within that array. So effectively, what's interesting in here is that this becomes a relative pointer. It refers relative to the beginning of that array. And every time you want to access the left subtree, you would have to literally just do that, right? So we have a node, you have a root, and then to get the left subtree, you'll have to do node pool root left, and there you go, you got the left subtree. Right, and the advantages of this sort of approach is actually quite cool. One of them is you can make the pointers way smaller than they are, because on the modern 64-bit architectures, the pointers is actually 64 bits, but here, since it's just an index relative to some absolute address, I can make it as big as I want or as small as I want. Thus, if I have a lot of nodes, I could compress, a lot of memory. So this is one of the things I can do. Another cool thing I can do is serializability, right? Essentially, if I do not refer to the memory in absolute values, I can just dump this entire array to file, right? I can dump it to file and then load it up, and it's going to be the same, because like every time you run the program, position of this thing may be actually different. You never know where exactly it is located in the memory, and you don't have to if you're operating in terms of relative values. Right, so this is kind of the things you can do. I've been doing the version of that in my C++ programs for quite some time, I'm sorry. And yeah, so apparently Jai has a similar thing built into the language. But it's rather interesting. So Jai is using a different point relative to which it is computing the pointer. Right, so the way it works, it's actually storing the relative pointer stores the offset relative to the place where this variable is located. Right, so this variable is located somewhere in the memory, and within itself, it stores an offset to the left or to the right on how you have to move. So essentially, if you have some sort of a node, right, and you want to go to the left subtree, what you will have to do, right, essentially, you will have to take the left variable, take a pointer of that thing, you take an absolute pointer to that specific variable, and you convert it to a pointer to a character so we can do all of the pointer arithmetics in bytes. And then you offset by the value stored within that variable. So, of course, you can address less memory to the left, to the right, but you also take up less space to store that. So this is actually pretty cool because you don't even have to know the beginning of your sort of pool array. The variable itself is the center, right? And you can go left and right. So this is how Jai handles relative pointers. But it actually handles that a little bit more smart because it uses a special encoding. Right, and this is precisely what I would want to explore today. And I think the best way to explore Jai relative pointers is actually to implement them in C. Because in C we'll have to work with them explicitly. So Jai, when you work with the Jai relative pointers, like there's a lot of stuff that Jai does implicitly. Like all of this stuff, like taking the absolute value, then offsetting, all of that is going to be completely implicit and generated by the compiler. So to actually expose all of that, to make it more explicit and visible, I would like to implement all of those ideas in C. And maybe come up with some sort of macros and stuff like that, right? So, and then once we, explore that in C, we can re-implement the same code in Jai to sort of compare how it would look like, how it looks like when we don't have that built into the language, and how it looks like how it's built into the language. Does it actually saves you on the boilerplate and stuff like that? Does it make it, more robust and less error-prone? You know what I'm talking about? So yeah, that's actually a pretty cool idea. And when you use the the variable itself, the address of the variable itself as the the beginning of the relative point relative to which you're computing everything, you still have the same advantages, right? So you still have a pretty pretty good serializability, pretty good serializability, and also you save up on space as well. Reverse engineering Jai compiler. I'm not really reverse engineering Jai compiler. I'm actually going off from the description that is given in the documentation for Jai. In the documentation for Jai, there is a how-to on how relative pointers works, and they even explain how exactly they work, like what kind of bit operations they apply there and stuff like that. We're gonna explore all of that today. All right, so let's actually implement like a very simple binary tree generator, right? So we're gonna have a text, and I'm gonna just have a node, right? So I'm gonna just implement all of that with absolute pointers just to have something going, right? So we definitely gonna have a node pool and stuff like that. And what do we want to do? First of all, I want to be able to allocate the node within this pool, right? So I need to be able to track how many nodes are already allocated. So what I'm thinking is that maybe I'm gonna put that pool into a structure, right? So let's actually define struct, and that struct is a node pool, right? So and in here we're gonna have, I suppose, nodes, right? So this is the nodes, and how many of them we already allocated, right? So this is the nodes, and this is the size. Maybe I'm gonna put size at the beginning, right? So the beginning of memory we have the size, and then we have the nodes themselves. Hello everyone, welcome. How are you guys doing? Okay, so and in here I'm gonna just allocate the node pool in the global static memory. So this is a node pool and it's static, and also gonna zero initialize this entire thing. So let's create a procedure, node pool alloc, right? So, and this thing is going to basically allocate the node within that pool, right? So that's the only thing it's going to do. So it will return us the absolute pointer, Right, so, and how we're gonna do that? First, we need to assert, right? We need to assert that we still have some space within the pool. Right. So, by the way, I think it makes sense to actually accept that pool as a parameter. So maybe you're gonna have several pools, right? So let's actually do that. Node pool, let's call it NP, right? So this is the node pool. Let's assert that the size of the pool, the amount of allocated nodes, is actually less than the node pool capacity, right? So this is the node pool capacity. Right, after that I'm going to take the last node, right, so this is the node, right in here, and I'm going to take a pointer to it, so that's the node we'll have to return in here. Right, after we've taken it, we need to increment the amount of nodes we have allocated. So here you go, we implemented a very simple linear allocator, right, so we just bump the counter and there you go. Very simple allocator. Maybe it also makes sense to zero initialize the entire thing, because why not, right? So it's actually quite cool if the allocator, mem sets to zero everything for us. All right, so Elimint0216, thank you so much for 6 months of tier 1 subscription. Thank you. Always happy to watch the stream. Relative pointers today fun. Yeah, they're actually kind of interesting. So this is actually a very cool technique. And it's extremely useful, and it's pretty cool that there are languages that support that, like, natively built in. Okay, so all right, so let me try to compile this entire thing. I'm going to create build.sh, right? So a simple script that is going to build everything in here. So let's do clang w-all w-extra. So I'm going to enable as many warnings as possible, and I'm going to try to compile this entire thing. So I'm also going to set xe, so essentially it will trace, it will print each individual command it's executing, and also it will fail the whole script on the first failed command, right? So that's what we're going to be doing in here, and let's mark this build script as executable and run this script. As you can see, it is printing the command that is currently executing, and it has a couple of warnings, a couple of errors that we'll need to fix. So assert, we need to include assert. Let's also include stdlib just in case, because usually you want to have that. All right, so memset is located in string as far as I know, and this thing is not zs, it's sz, right? It stands for size, and we have unused variable in here because we never actually use it. So for instance, here I can do the following thing. I can create a root node pool alloc. So this is the node pool. I want to call it something like global node pool, right? And let me go here and say it's a global node pool. And in here we can print something in here. Right, so we're gonna print the pointer, the absolute pointer to that specific root, and let's try to execute. Okay, so that's the pointer, that's the absolute pointer. Okay, Zaris, thank you so much for tier 1 6 month. Yo, thank you so much. Lumis, thank you so much for 2 months of Twitch Prime subscription. Hey, Tony, I really enjoy watching your videos and streams. Thank you, I really enjoy making them. All right, so let's go. So we probably want to also set the text in here, right? So I made the text actually fixed, right? Because it's because it makes it a part of the node. It also makes it limited because we cannot store more than 32 characters, but that is fine. I don't plan to store an infinite text in there. So how we're going to be storing the size of that string, right? So we can allocate maybe additional variable that stores the size, but maybe we can make it null terminated. We can basically reserve last one character always for null, right? And that way, yeah, it is always null terminated. I think for this specific thing, it's going to be fine. Right. Yeah, so it's a fixed string, but at the same time it is compatible with null terminated strings of C, and we are programming in C, so it kind of makes sense. You know what I mean? It kind of makes sense. So let's create a function that will do that for us, right? So maybe it's going to be node set text, right? And it's going to accept the null terminated string, hello world, and we'll do everything to just set that text properly into the nodes, because we also need to be able to handle like overflows. What if we're trying to set the text that is bigger than 32 bytes? So we probably have to truncate it, right, and don't save everything, because otherwise we're gonna have a buffer overflow, right, and some Rustition out there is gonna have a heart attack because of that. So we have to prevent that. All right, so let's do the following thing. Node set text. We're gonna accept the node, and we're gonna accept the text sister. We're gonna add the suffix sister to indicate that it's a C string. And what C string means, it means that it's null terminated. Right? So we sort of documenting with the names of the variable. It's almost like Hungarian notation, but it's not really Hungarian notation. Potato passing by, thank you so much for 2 months. Okay, so let me see. So what we need to do is essentially we need to see if the size of the text is not overflowing the capacity, right? So, but to do that, we actually need to compute the size of the text. So strlen text sister, right? So let me see. If n is greater than size of node text, so that will give me the size of the entire array, but we also need to preserve one character for the null terminator, so I'm going to do -1. If it is greater than the size -1, we'll have to set this thing to that specific value, right? So, and then after that we can quite easily do memcopy, right? Memcopy node text, text sister, and we copy exactly n characters. But we also need to make sure that it's null terminated, so I'm gonna do memset of node text with size of node text, just to make sure that it's all, you know, null terminated, and then I'm gonna copy it, right, like so. There you go. So here we have not pull alloc, and then we set the text. Maybe it would make sense to somehow combine these two functions, right? So maybe we could do node pull alloc with text. So we allocate and simultaneously set the text for this entire thing. Hello world, right? So that doesn't really sound like a bad idea, I think. Alright, so okay, so here we have to provide the node pool np const char text system, right? And what are we going to do? So here I'll have to return the pointer to the node, right? So this is the node, this is the result, and node pool allocate. I'm just allocating a new node, and I'm simultaneously setting it text to the provided text. Right, there you go. And then I want to return this result. There you go. So it would be also nice to have a facility that prints the tree, right? So since we have tree in here, let's actually do something like print tree. So it probably should accept the file into which we are printing everything, right? We're going to be printing into the standard output, and also the root, right? So this is what we need to have in here. Print tree file. Let's call it stream, right? So this is going to be a stream. and we're gonna accept the node, maybe by constant, maybe it doesn't matter, so I don't really want to go into the const correctness right now. Let's actually do something like unimplemented, right? So let's actually mark this thing as not implemented. As not implemented. All right. So let's try to compile this entire thing and see where exactly it fails. Let's implement not implemented. Right. 1, 2, 3, 4. So we're gonna 1, 2, 3, 4. Print f. We actually have to print the std error. So this one is going to be the file in which that happened, the line on which that happened, and we're going to say unimplemented. So the file is file, the line is line, and then we're going to exit with 1, right? And then we're going to just do this entire thing. Alright, so we have a couple of unused things in here, so maybe I'm going to actually mark them as unused. Unused stream, unused node, and unused is essentially a thing that is not used. Okay, so as you can see, this thing is not implemented yet. Okay. Cool. How are we going to be implementing all of that? So I suppose we're going to do the following thing. So maybe I also need to keep track of the level, right? So because I also need to indent things, if you know what I mean, right? So I need to properly indent things. Okay, so when I'm printing a node, right, depending on the level, right, I'm going to do the following thing. Size t less than level plus I, and I suppose I'm going to do the following thing. So each level is going to be 2 spaces, right? So each level is 2 spaces, and I'm print that into the stream. So after that, I want to print the text within the node, right? So we're going to do fputs node text also into the stream, and then we're going to do fputc new line, right, into the stream. So we're just printing the current node, right? So the text of the current node. After that, we have to recurse to left subtree and right subtree. So we have to do print tree, stream node left, level +1, and node right. But we probably have to do that only if left and right subtree are not nulls. So we have to do if left subtree is not null, and if right subtree is not null, only then we do recurse and we continue printing. Right, as soon as we encounter that they're null, we shouldn't try to do that, I think. Otherwise, we may try to dereference a null pointer, and another rustician out there is going to have another heart attack, right? So we want to prevent that as well. Okay. People are discussing white spaces. Very interesting. Okay, so let's go ahead and try to execute this program, right? Or at least compile, right? So it doesn't compile because here I have to specify the 0. Unfortunately, I don't program in C++, right? In C++, I could have done something like this, but in C, in pure C, it will not compile. C does not support default arguments. So the funny thing is that compiler knows what is the default argument, but it also knows that C doesn't support them, right? So it recognized the feature that I'm trying to use, but it doesn't allow me to use that because no, this is not C++. Right, it's especially funny, like the compiler knows the feature I'm trying to use, but it just can't allow me to use that because otherwise this is not a C++, this is not a C anymore. As you can see, we have hello world, right? So that's basically what we have. Then we can just go ahead and maybe allocate more nodes, right? So for the left subtree, we can do left is going to be equal to global foo, and right is going to be bar, right? So I'm allocating subtrees for the root. as you can see, so it actually indented all of them more or less correctly. Notice how I, well, I mean, yeah. So the cool thing about this, like a pool, instead of using malloc and free, is that because I never have to deallocate anything, right? Because I'm allocating in the static memory, I'm technically never calling malloc. And since I'm technically never calling malloc, I never have to call free, right? So I'm not leaking any memory, right? So quite often people don't like to program in C because, oh, it's so difficult to manage the memory. You have to call malloc and you should not forget to call free, otherwise you're leaking the memory. But people then do not realize that you never have to call free if you never called malloc. Think about that. And I'm not even joking. I'm not trying to make a joke or meme about, like, this is like a genuine thing that I'm trying to tell you. You never have to call free if you never called malloc. If you architect your entire program around the idea to reduce the amount of mallocs as much as possible, you actually have a good time of not managing memory at all. Like, you just don't. This is like, and a lot of problems that you have with memory management in C are kind of eliminated. They just don't exist. So yeah, think about that. Why the guys create Rust then? Well, you have to spend, you know, investors' money somewhere, because Mozilla as a company have a lot of investors, right, with a lot of money. So they invest into that company, and you have to spend this money somewhere. You have to burn it on something, right? So that's what I'm joking, by the way, this is a joke. So what I was talking about memory management before was not a joke, right? I was trying to genuinely share my knowledge. Whatever I said about Mozilla, it was a joke. This is already irony. So I noticed that people quite often do not distinguish when I'm actually joking and when I'm not joking, so I'm telling that explicitly to you, just in case. All right, so... you know, I think we need to generate like a bigger tree. Not bigotry, but, you know, bigger tree. You know what I'm talking about. So we need a bigger tree. The tree that is bigger. So how can we do that? We can actually just do that recursively, right? So we can say, okay, like create a tree of the depth of 3. Right, so we don't really want to go too deep because it grows exponentially, right? So it's an exponential explosion. So maybe like 3 or 4 levels. But then we'll have to generate random text. Every time I need to generate a random text, I usually pull out my list of fruits, right? So I have a project called Gym, which is actually a pretty cool project, by the way. So it's an immediate JSON serializer. So essentially it's a library that allows you to write this kind of code, right? So you sort of like describe JSON in an immediate style, like immediate UI, and this library generates you like an actual JSON. So with this library, it's actually a pretty cool library. You can have a tree, just like a tree data structure. You can iterate through that tree data structure recursively and call corresponding functions in here, and you can automatically turn it into JSON. Like you can automatically serialize it into JSON. It's actually quite convenient, and it's like a very simple C library. I do recommend you to check it out, right? So in here, for the tests, I have an interesting file called fruits.h, right? So if you open that file, it's literally a list of fruits. I don't know what you expected, but this is literally a list of fruits. Like I have a lot of fruits in here. So I usually use it for different kind of tests. So I also stole the list of fruits in here. Right. So let's actually download it. So we're going to be using this list of fruits. Fortran Lives, thank you so much for tier 1 subscription. Thank you. So, okay. I'm going to just download the list of fruits. Yes. Let's take a look at what kind of fruits we have. We have honeyberry, huckleberry, jackfruit. Are those really fruits? I know lemon. Lemon is a fruit. Okay. Oh, look! This is the creator of C++. I didn't know he was a fruit. Sorry. Alright, so let's actually try to hook it up into the main program. So fruits.h, and how many fruits do we have? So we can try to do the following thing. So we have a fruits count. Alright, so let's actually iterate through this entire thing for size I, less fruits count, and we can just print each individual fruit in here. So fruits I, there we go. And here are all of the fruits. I especially like ugly fruit. I don't know, what, is it so ugly? Is it really so ugly? Okay, so, and essentially now what we can do, if we want to generate like a random fruit, right? So you want to generate a random fruit, you take the amount of fruits, right? So fruits count, and you just generate a random number within the range of these fruits, and you get a bunch of random fruits. So we can generate 10 random fruits, right? So here's the 10 random fruits. If we also initialize the random number generator, right? So we're gonna get 10 different fruits each time. So they can be actually repeating themselves. Right, but as you can see, we get different fruits, which is kind of convenient. So we can use them to generate different, different texts for the nodes. She was subscribed with Twitch Prime twice, which is kind of weird. So this is kind of strange. So as you can see, she was subscribed twice. I don't know how, I don't know why, but I really appreciate. How do you say that? Twicely appreciate? Is that even a word? I'm not sure. Doubly appreciate. Right. It is actually called ugly because it is ugly from Wikipedia. Nice, thank you. That's very interesting. Jeff Bezos special. Yes, it is. Destroy computers. Thank you so much for the 39 months of tier 1 subscription. Hello, epic relative streamers. Thank you. I'm not an absolute streamer anymore, right? I'm just a relative. Oh, you mean like relatives? Okay, I see. That's actually a very interesting play on words. Alrighty. So let's generate a random tree. Right. Let's call it random tree. And I suppose we're gonna just take, yeah, something like this. It is going to accept the node pool, right? So because we're gonna be allocating the nodes within the pool, right? And I suppose we're also gonna accept the level, right? So because we wanna generate the tree of a particular level. So that's definitely what we wanna do. How are we gonna be doing all of that, right? So, I need to generate the root, right? So this is going to be the root, and I'm doing node pool alloc with the text, right? I'm allocated into NP, but the text I'm going to be using, I'm going to be doing fruits, rand, fruits count. There we go. Then I need to call this function, this specific function recursively. So I'm going to be generating the left subtree with the same allocator, but with the level less than 1. Right, and then I'm going to be doing the right subtree also with the level less than 1. And that way I'm sort of going recursively and I'm just generating the tree until I ran out of levels or ran out of memory. Right, so, but luckily every time I allocate, I actually check if I have enough space within the pool. So if I try to generate more than 1024 nodes, it will actually crash. It will, fail the assertion. And it's not that difficult to actually do that. I just need to generate the tree with the level of 10. Right, so 2 to the power of 10. Right, so yeah. If I try to do that, if I try to generate more, it will instantly fail. Right. So, and in here I probably want to do the following thing. If the level is equal 0, then I just have to return null, right, indicating that that's it, so we don't have anything to generate. Okay, so let's go ahead and just simply generate a tree. Right, so I'm gonna keep srand to, you know, randomize the random number generator, and let's generate a random tree. I'm gonna provide the global node pool we're gonna be allocating there, and let's generate like 3 levels, right? So this is gonna be node, root, and then I'm gonna try to print the tree into the std out, right? Is it gonna work? Let's actually see. And it doesn't even compile. I'm super happy about that. What we have to do, we have to return. Okay, so we have another thing in here. Too few arguments, we have to provide the level in here, and look at that. So I promised you that it's gonna be 3 levels deep tree. There you go, it is 3 levels deep tree. So you can clearly see that. Isn't that cool? Isn't that cool? I think it's pretty fucking cool. We can actually increase the amount of levels. Let's actually do 4. Now this is 4 levels of the tree, and then we can have 5. And if we have 5, as you can see, it grows exponentially. So I think 5 is more than enough. Right. So that's pretty cool. Sam J and which? Sam, I don't know how to pronounce correctly your name, but yeah. Okay, so a passion fruit. A passion fruit. Okay, that's pretty cool. So, but all of that is done using absolute pointers, right? All of that done is using absolute pointers, and which means that you can't just save the pool into the file system and read it back and expect all of the pointers working correctly. Maybe it will work correctly by accident, but I actually doubt that. It's actually very interesting. It is actually very, very interesting. We can try to do that. So let's actually do something like save node pool to file. And we're going to accept node pool, right? So this is np. And we're going to also accept the file path. All right. So in here we can open the file. Right, so it's going to be out. fopen file path. Right, so this is the file path. We're gonna open it in a write mode binary, right? So, and if that failed, right, we'll have to print something. So let's actually do the following thing: std error could not write to file s because of that file path str error. Error no. So basically error no contains the number of an error, and str error converts that to a string, and we're printing the reason why this entire thing failed. That's what we're doing today. All right, so and then after that we're gonna close this entire thing. So, and dumping this entire thing is rather straightforward, I would say. We can just use fwrite. Actually, fwrite designed specifically to save arrays of items. Right, so notice how it accepts 2 sizes. First, it accepts the size of the element and then the amount of elements. And quite often, people just like use one or another and set 1 to 1. Right, but here it is designed specifically to save arrays. Right, so I can take an array, np data. The size of the single element I'm saving is the size of node, and the amount of elements I have is np as size, right? So as you can see, it fits perfectly into our purpose, right? So we're saving an array of things, and in here it also returns how many of things it saved. Here we can just you know, maybe assert that it's saved exactly as many as I have in here, and if I got an error, right? I can also print this entire thing, why not? There we go. Alright, so we have some problem here. Is it not called data? I think it is called nodes. It is not called data, it is called nodes. Okay, that makes sense. What else do we have in here? We have to include error no, right? and f close, it's not called f, it is called out. Okay, cool, but we never actually saved anything, so let's actually generate a random tree, then let's print it, and call save node pool to file. Right, so essentially in here, we're going to be saving global node pool to, let's call this tree bin. Maybe we can call it fruits bin. Alright, so, and it failed. I'm actually surprised that it failed. Is that because it really didn't save as many as I would expect? Let me try to print this entire thing. So I'm gonna do sz, n is equal to that, and npsz is equal to that, and npsz. So something was not particularly correct, and I'm actually surprised. So I forgot to put a new line, so it flashed everything. And yeah, it returned 0 because I was trying to read instead of writing them. So I was supposed to write them, and as you can see, everything worked perfectly. Okay, so we have a binary file in here. So let's actually take a look inside of that file and see if we can distinguish anything there. It's actually rather interesting. So what is this called? Relative pointers. So hex editor fruits bin. Okay, so as you can see here, if you look in here, we have the name. Right, we have the name, and then we have padding with 0, right? We have padding with 0 until we get the pointer, and the pointer is supposed to be this long, right? So this is the left subtree, this is the right subtree, and then we have pitch, which actually starts here, right? So yeah, that makes sense. So we have this big string, right, 32 characters, and then the left subtree and right subtree, and all of that, the absolute pointers within the memory at the moment of executing the program. All of them are absolute, and as I already said, we cannot rely on them working after we try to load up that file. We can actually try to do that, right? So we have a function that saves node pool to file, but let's actually implement load node pool from file. Who said we can't do that? We can try to do that, right? But it's not really clear what we have to consider the root in that case. But I'm gonna assume that the root is allocated the first, so the first element of the node pool is going to be the root. I think it's a very safe thing to assume in this particular case. What do you guys think? Right, so we can kind of do that. I program Pascal for work. I can't imagine why you would willingly do that to yourself. I do not believe you. I don't think you actually program in Pascal at work. You're probably working in one of those nasty extensions of Pascal, like Object Pascal or Delphi, which are in fact unbearable, and they're basically massacring the original idea of Pascal being like a very simplistic language on the level of C. So I do not believe that you program in the original Nicholas Wirth Pascal. Nobody programs in that Pascal anymore, unfortunately. Except me. I programmed in it on one of the previous streams. So, alright. Let's continue. I ran out of water, unfortunately. I really like the original Pascal, right? The OG Pascal. Yes, Bitstream is actually correct. I really love it because it's basically like a better C. Right, so it's more strongly typed. It allows you to do one of the things that I do quite often in C, which is basically indexing arrays with enumerations. It has that feature built in. It allows you to strongly to index arrays with enumerations in a strongly typed manner, which is not really supported in that many languages these days. Like the only other language I know supports that is Ada. Right, so there's only 2 languages I know for sure support this kind of stuff, like indexing arrays with enumerations in a strongly typed manner, where it actually checks the enumeration that you're trying to index array with. It's only Pascal and Ada, right? I don't know any other language. Maybe there are some other languages, but I just don't know them. All right. Okay, so let's continue. So this is going to be a node pool into which we're like loading everything, and we don't really know like how many nodes we have there. That's kind of the problem. Though, we can compute the size of the file, right? We can compute the size of the file, and based on the size of the file, compute the amount of nodes. We can take the size of the file in bytes and divide it by the size of the nodes, and this is how many nodes we have in there. So this is one of the things we can do, which is rather a good idea, I think. So let's go ahead and do that. So file path. All right. So out f open, right? So we open in the file. So this is the file path. We opening it for reading in binary. So I'm gonna copy paste some of the error handling in here. So could not read from file. That's because of that. So and now the time has come to figure out the size of the file. Right, so the usual way we do that, we use fseek. So when you open a file, it has a cursor. So we set the cursor to the end of the file and we get its value, and that's the size of the file in bytes. Right, so we have to do fseek. We provide the file and we seek to the end. Right, so we seek to the end. And then we try to get the value of that cursor, right? So m is basically the size of that file, right? And then we actually have to go back, otherwise we won't be able to read that file. Seek set. Okay, interestingly enough, we need to assert that m is divisible by the size of the nodes, right? We need to assert that. If it's not, that means we have the file of the wrong size. So after that, we need to compute how many nodes are we going to have in there. So this is going to be sz, and I literally just divide m by node. There we go. So this is sz. But here's the interesting thing. Node pool has a limited capacity. So another thing we want to assert is this thing not being greater than the node pool capacity. If it is greater, well, it is an error, it is invalid file, so we don't really want to read that. Okay, so after that we can try to read this entire thing. So let's go ahead and do that. So we're gonna use, you know, a similar function, but fread. It literally has the same interface, in fact. Right, so it literally has the same interface, and here we can also assert that we did that, and then we're going to close the file, right? So it's not that. All right, so let me try to compile this entire thing and like make sure that it compiles. Cool. So now, what I want to do, I want to create another entry point, and in that entry point, we're going to try to read. Let me actually take this name and maybe save it to some sort of a constant, like fruits bin path. Right, so let's take a fruits bin and save it in here, so we can refer to that fruits bin in the same manner, right? And if I change that name, it will change everywhere where I refer to it. Okay, so what I want to do, I want to load the node pool from file. I can't actually go. Yeah, there we go. I'm going to be reading everything into the global node pool, and then fruits bin path. Bin path, there we go. We loaded this entire thing up. And then, as I already said, I'm going to simply assume that the root is the first node, right? So this is the nodes 0, and this is the root. So, and then I'm going to try to print this entire root. And if everything went according to the plan, the program should succeed. So there we go. And it didn't segfault, but it didn't print anything either. And you know why? Because I never actually run it. So that's why, because I only compiled it. Alright, so let's actually try to do that. And yeah, that's very cool. Something actually failed. So I have to check for that. Right, it's a reversed condition. Right, as you can see, it segfaulted. That's exactly what I wanted to see. It's a very, very rare situation when I explicitly wanted the program to segfault. I spent like 10 minutes writing this piece of code that is segfaulting, and it does in fact segfaults. I call it a success. Alright, what do you guys think? So this is pretty expected because again we're using absolute pointers, right? We use absolute pointers. So now, if we try to switch to relative pointers, this problem should go away, right? This problem, in fact, should go away, but we're gonna do that after a small break, after I make a cup of tea. So, okay, let's continue. So, as already promised, right, we're gonna implement the Jai-style relative pointers, right? So how are we gonna be doing that? So I think the coolest thing about such pointers would be that we can take these two pointers and essentially fit them into 64-bit integer, right? So essentially it's going to be int 32 and int 32, right? And both of the pointers, right, essentially fit into the 64-bit pointer, right? So I'm using signed integers in here. This is very important. Jai does the same. Essentially, it allows the pointer to point not only forward from the place where it is located, but also backwards, right? So it addresses the range to the right and to the left, or to the left or to the right for you, because you're watching looking at me through the camera, right? So, and essentially how we're going to be doing all of that, right? So if I want to, let's go ahead and simply get rid of this entry point that loads the file and leave only the thing that saves the file. And let's try to compile. Since we changed the definition of this entire thing, it will fail in all of the places where it's trying to work with the pointers, and we're going to fix those places and refactor everything. Right, so, and surprisingly this shit kind of worked. Well, I mean, yeah, that's kind of surprising. So, and the reason why it works is because all of those things are warnings, so C allows a lot of implicit conversions. So let's actually fix that, but by making warnings errors, right? And now it should not compile. All right, so we're gonna be doing here. So I'm printing the tree. I'm not sure if printing is something that I want to do right now, right? Because printing will require to convert a relative pointer to the absolute one to continue the recursion, right? So I think I'm going to do the following thing. I'm going to comment out the function, right? I'm going to comment out the function that prints, and I'm going to continue compilation because I want to focus on converting absolute pointers to the relative ones. Right, so I want to focus on that operation first. Okay, so this is the random tree, and this is actually a very interesting one. So as you can see in here, we get an absolute pointer, right? So this is the absolute pointer, but when we try to assign it to left, we can't do that because left is a relative pointer. So what we need to do, we need to take this thing, right? And then take a pointer to the location to the left and subtract it. That way we get an offset, right? To the left or to the right, depending on where we're located. But we want all of this pointer arithmetic to be in bytes, so that's why we have to convert all of these things to pointer to a byte, right? In our case, character is a byte, though we can be a little bit more explicit and we can replace character to uint8_t, right? So as you can see, here is one pointer, the absolute pointer, and here is the pointer to the location that stores a relative one, right? So after that, we have a distance, right, in bytes, which then we convert to uint32. Right, and this is how effectively we convert an absolute pointer, to a relative one, a relative to where the left is located. Does this operation make sense? Does this operation make sense? We have to do the same thing for the right one. Right, so this one, I'm going to convert this thing to a pointer to U8, and then, so I have to also make it a pointer, int8, t underscore, right, and then I take a pointer to the right, so I subtract those two things, and then I do uint t, right. So this is a little bit cumbersome. As you can see, right, it's a bit cumbersome, so I think it makes sense to wrap that in a macro. This is one of the reasons why you probably want to have some sort of a language support for this kind of pointers, because you don't really want to do this kind of thing manually all the time, right? What I'm doing here, I'm just casting an absolute pointer to a relative one. And what if I make any mistake in here? This is very error porn. This is straight up error rule 34. Right, so that's what it is. Cheers, by the way. I'm gonna keep drinking my piss. Yeah. Error porn. Error porn. Okay, so how are we gonna call this thing? Let's actually call it something like ABS, not BAS, but ABS to rel. But we're gonna say that it's specifically 32, right? Because you can actually have relative pointers of different size, right? So in here I have 32 bits, but what if I had 16? Of course, I would address a smaller range, but then the pointers themselves take up less space, and maybe I can have relative pointers of the size of 8. These pointers can't really address that much, right? But still, right, they're going to be pointers. So in our case, we're going to use 32, and to indicate that we're working with the pointers of 32 bits, I'm going to put 32 in here. This is a very readable macro. Maybe I should not capitalize that because, like, it's... Yeah. So the digits at least stand out, right? So you can kind of read it a little bit better. I think ABS to rel with like small letters is a little bit more readable, right? If we like to talk about readability. Okay, so here I'm gonna accept, and it's rather interesting. I'm gonna accept the absolute pointer, right? So this is absolute pointer. And then I'm gonna accept relative location, right? Because I'm not accepting really a pointer as a value. I'm accepting the name of the variable that stores the relative pointer. That's a huge difference. So let's actually call this something like aptr and then rlog, right? So aptr is absolute pointer, right? The value of a memory address, right? And then we have our log, relative location, right? Maybe location with the relative pointer, the name of the variable that stores the relative pointer, the relative address, right? So this is a huge difference, because one thing is a straight up value, another one is more like an L value, if you know what I mean, right? It's more of an L value if we're gonna use this terminology in C, right? So, and in here, what I want to do, I want to convert the absolute pointer to the pointer of uint8, so aptr. Then I'm gonna subtract the pointer to rlog, right? So, and that's the reason why I accept the name, because I want to take a pointer of this entire thing. Right. And then I'm effectively assigning it back to uint, so that means I have to... maybe it was fine. I just don't know if that's the way I want to do that. I think that's the way I want to do that. Why not? Right, so it made it a little bit more readable. ABS to rel32. And then I'm going to accept this thing. Though, interestingly enough, I might as well also assign it, right? Because the only purpose I take this thing is because I want to assign it. So I want to do the following thing, rlog. And this thing becomes straight up a statement. right? And to actually say that I'm assigning the right-hand side value to the left-hand side, I think it makes sense to actually swap their location. And now what I'm effectively doing is, right, ABS to rel, right? So that makes sense. That's actually pretty cool. So that way I can just do right, and look how readable it is. It still looks like shit because the language doesn't really have a support. But anyway. So what's interesting is that usually in the macros you want to wrap all of that stuff in parentheses, right? Because those things can be expressions, so you want this thing to be parsed properly. Right, and there we go. So we've got this stuff, and let's continue compiling. So expected expression. But this is not particularly an expression. Maybe this is because I should not put parentheses in here. Expected expression from uint8, and oh boy, what do you want from me? I'm really not sure. What do you want from me? Expanded from macro. Use of an okay, so it's basically an error within the error, right? So I should have included the stdint in here. Thank you, Sigcompiler. Very cool. Right, so and we have an unused variable in here, which I don't know. I can say that it's unused, right? So it's totally fine for this variable to be unused, and everything seems to be working. So yep. So now we have all of that stuff saved to the file, right? And look at that, the file actually became smaller. So the previous file, I don't know for sure, but I think it was around 1.5, right? I'm pretty sure it was around 1.5. In fact, we can make it even smaller. We can reduce the size of the text, right? So we need to know what's the biggest size of the fruits, right? So I think we can quite easily do that. So we can do something like int main, so biggest fruit, flushed. Okay, so we're gonna iterate through all of the fruits. 0 fruits count plus I, and if, so maybe I should probably save something like this: n strlen fruits I if n is greater than the biggest fruit. We found the biggest fruit, right? And then we can print this thing. Biggest fruit has length equal to 0. Right, and we're gonna just straight up print the biggest fruit. And what we're gonna do, we're gonna try to find the closest point, power of 2. Okay, so 17, and the closest power of 2 is 32, which we already have. Right, so it's kind of funny, but I mean, it is what it is. So interestingly enough, we can put 24 in here, and this is actually kind of cool. So 24, and then additional 8 bytes from 2 pointers in here, right? So, and we have exactly 32 bytes. So with these kind of pointers, we can actually control exactly the size of the structure, which is kind of cool, I think. What do you guys think? I think it's actually pretty cool. Let me see. So let's try to generate the fruits with the new size. Correct. So yeah, it became less than 1 kilobyte now. Right, so it's kind of interesting. So we're talking about like a couple of bytes, right? A couple of bytes, but we have a lot of nodes. And all of this like small amount of bytes, they actually add up when you have a lot of nodes. And that's why we can like actually change this size. And furthermore, the amount of nodes grows exponentially based on the level, right? On how deep the tree goes. So one additional byte per node on an exponential level of things adds up really fucking quickly. That's why even with the modern computers, we may want to care about this kind of thing sometimes, not always, but I mean, if you have a data structure that just grows exponentially, right? So that means your additional bytes will stack up exponentially as well. So yeah, I mean, if you're writing just like a website in React that doesn't really do much, you probably don't even care about this kind of stuff, but we're exploring serious software development in here. Okay, is it a common technique to use relative pointer? As far as I know, in game development it is, especially in not really game development, but game engine development, right? Because these days game development is just like throwing a bunch of assets in Unity and call it a day, right? So I'm not talking about that game development. I'm talking about the old style game development where people actually develop their own engines. And I mean, people still develop their own engines, right? Different companies and stuff like that. So was just writing some React, so it hurts. I do understand you because I write. Well, I mean, I haven't programmed in React for quite some time, but I have to do web development from time to time, and it in fact hurts. I do understand you, so I do understand you. So it is what it is, and it isn't what it isn't. Web is kind of painful. I do agree with you. Wow, people hating on web dev. Well, I would be surprised if people not hating on web dev, because that's a good sign that they have a Stockholm syndrome, right? If you're not hating on the web and you're a web developer, well, you probably have a problem. Straight up a Stockholm syndrome. You may want to work on that. So, anyway, so let's continue. What do we want to do? Now we want to be able to actually, how is it called? Dereference that thing, right? So we know how to convert absolute pointers to relatives to store them, and now we have to do the opposite thing. We have to take relative pointers and convert them to absolute ones, right? So that's what we have to do. So I'm gonna uncomment the print tree. As I already said, I didn't want to do that because I didn't want to focus on that. I wanted to focus first on absolute to relative. And let's go through the compilation errors, right? This one is rather interesting. So let me move this entire thing somewhere here. And what I want to do in here, right? So we actually accept an absolute pointer. Right, and as we print, as we recurse down, we want to be constantly converting relative pointers left to the absolute ones, right? So that's what we want to be doing. So let's implement rel to abs32, right? So rel to abs32. And let's define this thing. So as far as I know here, we don't really need anything else because we're using the location, the relative location, as the starting point for all of the arithmetics, right? So the rel to abs32 relative location. And as already mentioned, what we have to do, we have to take the pointer to that specific location and convert it to uint8. So all of the pointer arithmetic is, you know, in bytes rather than the items. And I'm going to be adding the value of that thing itself. Right, I'm adding the value of that thing itself. And interestingly enough, I need to convert it into the pointer of a specific type. In that case, the type of the node, but from this macro, I don't really know that type. So maybe another parameter that I have to accept is the, is the type, the pointer of which I'm trying to compute, right? Something like this. And because of that here, I'll have to put a node. Okay, so yeah, we essentially implement everything. So I'm not sure if I have to do like our lock in here because it's only for expressions, but I'm actually taking L value. So L value as an expression. Do I really care? I don't know, maybe. We'll see. If that will create an error, like a problem, I'll fix that accordingly. So for now, it doesn't really create any problems, so whatever. And as you can see, it segfaulted. Interestingly enough, it segfaulted. And I wonder why. It's segfaulted. So it's segfaulted specifically on trying to print, right? So if I don't try to print anything in here, as you can see, it works. But if I do try to print, it doesn't work. If not left, you think it's because of that, right? So, but that's really strange, right? So essentially, if it's 0, if it's pointing to itself, right? If it is pointing to itself, it is going to be 0, and that means it's not going to continue. Right. Oh, this one is interesting. Wait a second. Right, so if we get a 0, we actually have a legit pointer, right? But then it should stop at some point in here. Okay, if the next one... So I want to understand precisely. So maybe that's what we have to do. Like if node equal null, right? So let's actually confirm that it is like that. So we have to return it like that. So and then we can just do it like this. Yep, and it works correctly. So it has something to do with 0, right? And representing null pointer with the relative pointers is actually rather interesting, all right? Because 0 with the relative pointers is a valid pointer. It is not null, right? So, and as far as I know, like people solve this kind of problem differently. Some people just say, okay, you can't point to yourself if you're using relative pointers, and that way 0 becomes the like a natural null, right? And the reason why you want to use 0 as the null even for relative pointers is because of this 0 initialization approach that I use and many other C developers use as well, where quite often you want to just take a structure, mem set it to 0, and it has to be a valid structure with the reasonable default values. And a reasonable default value as 0 for a pointer is a null pointer, a non-existent pointer. That's why even for relative pointers you want to use 0 as the null, right? Because it just makes sense, it solves a lot of problems, right? So, and so essentially, as I already said, what people do, they say, okay, you use 0 as the null, and because of that you can't point to yourself. But it's kind of a limited solution, right? Because sometimes you want to point to yourself. For instance, what if I have like a cycled linked list, right? And it has a one element, so it points to yourself, to itself. How do I encode that with the relative pointers? How do I do that? Right, and you know what's funny? Jai actually solves that problem, right? So it uses a special encoding that allows you to use 0 for relative pointers as the null, right? But it still has a null. Okay, so here's how this entire idea works. It's actually really cool. I really like how Jai approaches that. But as far as I know, that is not sort of like the final solution for relative pointers in Jai. John said himself that he picked just like whatever he had at the top of his head, or maybe, I don't know, he just picked one encoding, right, and called it a day, right? So, but he doesn't claim that this is the best encoding for relative pointers. It's just the encoding that he picked, right? So there could be maybe better encoding that actually makes it easier, more reliable, more you know, fast and stuff like that. So idea is the following. Imagine that we have a relative pointer of the size 8. So what's the range of the values for int 8? What's the range of the values? It's from -128 to 127. In fact, this is the case for all of the signed integers. All of these signed integers have this extra element on the left side. This extra element on the left side, which is kind of weird. So the idea that Jai has is, okay, let's actually pick this element as the null. Right, this is going to be our null. So the range now becomes, that available to us is from minus 127 to 127. We just lose one number. And the range itself becomes actually even, right? So it's from minus 127 to plus 127. And it's the same for 16 bits, 32, 64, whatever you call it. Right, but here is an interesting thing. So we say this is a null. So that means we need to come up with special encoding for relative pointers so that when you encode minus 128, it is equal to 0. Right. So what kind of encoding we can come up with? And here's an interesting thing. 128 minus 128 in binary is equal to 1, 0, 0, 0, 0, 0, 0, 0. So minus 128 is just one highest bit. So that's what it is. And essentially the idea is the following. When you want to encode a relative pointer to save somewhere, relative PTR, what you do, let's actually call it x, you just XOR it with this thing. And every time you want to do any arithmetics and you want to decode that, you do it again. So encoding and decoding is just like every time you XOR with this specific value. And that actually creates the situation when the encoded null is equal to 0. So when you take a structure with the relative pointers and mem set it to 0, they all equal 0, and 0 is an encoded null. 0 in encoded form is minus 128. So that works out. So that's basically how it works. And it works because XOR has a very interesting value. X XOR y is equal to x. So essentially by like XORing this value, you simultaneously encode and decode. Don't all negative numbers become positive? Yes, that's true. That's why before trying to add your relative pointer, right, you have a relative pointer, that's why before trying to add this thing to absolute pointer, you have to decode it. We XOR it with this thing only for storage purposes. And as soon as we need to do any arithmetic, we decode it and bring it back. So the reason why we have to do that is that why we have to decode it and store it in encoded form is because we need to compare it to null, to 0. You see what I mean? So that does not affect arithmetics. Right. So essentially we just map one range of values to another range of values where 0 is the null. So that's how it's done. And we sacrifice like one value at the left of the range. So that's how it works. And that's how, as far as I know, Jai does that. So essentially what we have to do now, when we do ABS, ABS to rel or rel to ABS, like in here, right? So here's the, we take a pointer and stuff like that. So what we have to do now, we have to XOR. So I'm going to use hex, right? So in hex, when the highest bit is set, is basically 8, 0, 0, 0, 0, 0, 0, 0, right? So this is in hex, is in binary, it's equal to 1, 0, 0, 0, 0, 0, 0. Right, so here I've got the value of the relative pointer and I encoded it. Then here, when I need to relative to ABS, before adding it, I'm decoding it back, and there you go. So now, when you try to do a relative to ABS and your relative, right, your relative is equal to 0, right, so you do something like node and x, right, so x is equal to 0, you try to do this thing, and as you can see here, the first thing that will happen is we're gonna XOR x with this value, which will turn this entire thing into 1, 0, 0, 0, 0. You will try to add that thing, and you will try to access the range after it, so basically you're trying to dereference null pointer. Right, so that's basically what's going on here. And that way, we can bring back the check in here if node is left, if node is right, and that should work. Because now, if the relative pointer is equal to null, its encoded value is going to be null anyway. Right, so let's actually give it a try and see if it's going to work. So something went wrong in here. I wonder what exactly. Expanded from invalid operands to binary operation. It's probably... Really? So it doesn't like this thing, but our lock operands to binary expression. Is that because I have to do something like this? Yeah, and it failed anyway. Fuck. So how many characters do I have in here? So I have add characters, so this is gonna be 1, 2, 3, 4. And in here we... Alright, my internet went down, so I'm now recording completely offline. So, because I really want to finish the entire thing. Okay, so we need to understand what exactly went wrong and why it doesn't work, right? So, because according to my calculations, it should work, right? So, essentially, we compute the difference between these two things, right? And then we XOR it, right? So we set the highest bit to 1, but I'm not sure if I'm doing this thing correctly. So it's 8 characters, 1, 2, 3, 4 bytes in here. We store everything, so I really don't know what exactly is wrong in here. I really don't. So interestingly though, if I don't print, right, let's try to not print anything in here. Let's try to not print, and I'm gonna even like comment everything out, and everything seems to be okay. And if we take a look at the binary, let's take a look at the binary. It's actually rather interesting. So here we have a grape. All right, and then we have actually pointers in here. So coconut starts at here. So the 4 pointers are in here, and here is another pointer. So here we have like 1 byte set to 0. Interestingly enough, so it's a little endian, right? So that's why this thing is set like that. Yep. So I don't really know what's the problem, right? So I don't see. It's probably something extremely stupid. I'm pretty sure. I'm really confident that this is something stupid. Very, very, very stupid. Okay, so I take a pointer to the location of this thing. Then I XOR the value stored in that location, and then I add it in here. I'm not sure. Am I doing the right thing? So maybe I'm computing the offset incorrectly. So that could be the case. Or maybe I made a typo in here. 1, 2, 3, 4. Wait, this is 10 characters, and this is 10 characters as well. Okay, so that's fine. I don't know why. For some reason I thought it's 11 characters. So it's something with print, so that means it's something in here. Damn. I don't see any problem. Like, what's the problem in here? But if I... Okay, so what if I bring this thing? I have a feeling that I do not understand how, like, what exactly is going on. Alright, so what is the problem? And let me also print this entire thing. Yeah, it's still seg faults. Still seg faults. And it actually shouldn't. If I try to print, d, where I take 0, XOR, that's kind of dumb, but let me actually do something like this. XOR 0, X, yeah. Something which is, yeah, it is in fact correct. Right, and then if I try to do this thing, it becomes 0. So everything works exactly as I would expect. Right, so everything's fine in here. So I take a pointer to the location, convert this entire thing to uint so I can do all of the computations in bytes. Alright, then I take the value inside of that location, I sort of decode it. So if it was like minus something, it would work. Right, and I really don't see, like, what the hell. So maybe I should like GDB step debug this entire thing. Yeah, so let's give it a try. Let's try to GDB step debug. So aka what? Expanded for macro invalid operands. Oh man. So is that because I need to do it like that? I'm going insane already. Wait, what? Why don't you like it anymore? So it kind of worked before now. Unassigned. Left, okay. Invalid. Operands to binary expression. But rlock is not that, isn't it? Rlock is uint, so it should work. I'm going insane. Okay. That's probably why you have to have a built-in support for this entire thing in the language, right? So you don't go insane like that. Alright, so let's actually try to GDB this entire thing because it's just like really impossible to understand. It's probably something with conversions and stuff like that. And all of those bugs are extremely annoying. Right, because you never really know like what exactly is going on there. Okay, break at print tree, right, and just to run this entire thing. Let's enable TUI, and let's take a look at the node. Right, so in the node, we have this thing. And let me see. Will we ever have... So let's actually try to generate a thing with a single layer. This instantly gave me an idea. All right, so we're gonna have a single layer in here. So that already gives me ideas. That's cool. All right, and it, yeah, so because then we can quite easily go inside print tree, run TUI enable, and I can print the node. Right, and that is a very strange thing. Right, why do we have this stuff on the left and the right? Right, where did that stuff come from? Where did it come from? Because all of this, both of these things have to be 0. So let me see. So when we generate a random tree, so I feel like So this is probably why it is happening, but when I allocate a new thing, do I not memset to 0 everything? I was quite confident that I memset to 0 everything, and that's precisely what's going on in here. I have a strange feeling that something went wrong during the generating a random tree, right? So we're generating a random tree incorrectly. So let's actually try to break there. So random tree, break random tree. And let's just try to run that and let me see. All right. So cool. I generated a root. And if I try to print that, everything is fine, which is kind of not, because I said generate it with this, with the text, and where is the text? I don't see that. So maybe we can display. Oh, here it is. I just didn't see it properly. I'm sorry. Right. So, and at the left I have 0. So I have to go deeper. Right. I have to go deeper. I think I know what is going on in here. Right, because we take an absolute null. Yeah, I see what's going on. We need a special, yeah, I didn't think about that. We need a special function that converts an absolute null to relative null. Okay, this took me 10 minutes to realize, unfortunately. Yeah, that's another thing we actually need. We need a special utility that converts absolute null to relative null, because you can't use the same procedure to convert absolute null to relative one. Okay, I'm really glad that I tried to debug it. So let's quickly try to fix that. So right now, the easiest way to fix that is probably something like this. If level is greater than 1, then go down, and if the level greater than 1, then go down. It's kind of similar, right? It's kind of similar to what we were doing in here, right? Yeah, that works. If this thing is that, if this thing is that, all right, and yeah, I think that should fix it, because effectively we're not going to go down recursively. We're not going to recurse in any of the subtrees. So that means it's going to stay 0, right? And everything should work accordingly. Let me try to compile. So everything works, nothing segfaults. Let's put 5 in here, right? And there you go. As you can see, we have everything working with relative pointers. So that's pretty cool. These are relative pointers. And the coolest thing here is that now I can load up this file back into memory, and all of the pointers are going to work. So everything should work correctly, because they are not absolute values. Okay, so let's actually try to do that. So I'm going to do this. Int main return 0. And we need to load node pool from file. Right, we're loading it from file. So this one is a global node pool, and we're going to be providing the fruit bin path. Cool. So as I already mentioned, we're going to assume the first element to be the root, and let's try to print the root. So this is going to be global node pool nodes 0, and we're going to take the absolute pointer in here, and we're going to start from 0 in here. There we go. So let's try to run this entire thing, and as you can see, we're actually reading it, and it's the same file. Right, it is the same file. So as you can see, it starts with Kiwana. I don't know what is this. Boysenberry. Passion fruit, and it keeps being the same, right? So because we're reading that data from the file with the relative pointers and stuff, right? So my internet is still down, surprisingly. Yeah, I think it's gonna stay down, so it's probably for a long time. Right, so yeah, so we use relative pointers. We use an encoding that allows us to use null relative pointers that actually zero, so we can use the usual null logic. And as already mentioned, as far as I know, Jai works precisely like that. Jai uses the same encoding, and one of the things I wanted to use to try to do in today's stream, right? It's a fly stream already, but anyway, is to preserve this binary file and write a similar Jai program that loads up the same file and iterates through the tree and see if it will work. Right. I want you to confirm that we match the Jai semantic when it comes to working with the relative pointers. So let's actually try to do that. So I'm going to create main Jai. Right, I'm going to create main Jai, and so I'm going to import basics for the text facilities, and let's create an entry point. Right, in the entry point, I'm going to do hello sailor, just to confirm that everything is working. All right, and I'm going to do Jai Linux main Jai, and I'm going to run the program simultaneously. It's going to take some time because it, you know, caches the disk and stuff like that, and there you go. All right, so we need to define a similar structure that we have in here, right? So let's define a node, right? That let's define the text, which is going to be array of U8. As far as I know, Jai doesn't have a characters; it just has U8. And let's define the left and right subtrees. Right, so the pointers in Jai are defined like this, but the relative pointers are defined with the additional tilde. And after the tilde, you also specify what's going to be the underlying type for the relative pointer. So as you can see in here, we use signed 32-bit integer, and you can do the same in Jai as well. So you say it's a relative pointer, but it's a signed 32 bits. Right, so let's actually try to compile and see if it compiles. Right, it has to be struct in here. Right, it has to be struct. Attempt to subscribe non-array. As far as I know, the size of the array is put in here, right? So it goes first. As you can see, it compiles, right? So this syntax is correct, and this is relative pointer, right? Okay, so now what we can do, let's actually define a pool, right? So node pool, and it's going to be an array of 1024 nodes. One of the things we would like to probably check is the size, maybe, of this structure first, just to confirm that, you know, it is what it is. Size of node. As far as I know, it's a size of node. So let me see. It's 32. It is exactly 32. Just like in a C version, right? Because 24 bytes for the text and 4 bytes for left subtree and 4 bytes for right subtree. Okay, so let's define a pool, right? So this is going to be node pool, which is 1024. Honestly, I don't think we need to have a pool, because Jai has a very cool function, right? So how to not really how to, but module file. Let me see. So read entire file. Right, it just like reads the entire file. We can go ahead and read the entire file. Who said we can't do that? Right. Fruits bin path. And fruits bin path is essentially fruits bin. That should give us this string. Content, okay. Right, if not okay, just return. We can say something maybe before returning. We can exit with 1 to indicate an error, and we can also say something like print could not, maybe error, could not read file this, which is fruits bin path. Okay. So in here, now we can try to construct like a slice of nodes, right? So we have a nodes pool, which is essentially a slice of nodes, right? And for the nodes pool, for the data, we're gonna set the contents data. This is the contents data, but we're gonna cast this entire thing to the pointer to the node, right? So that's what we do here. So then the count is going to be the content count, but divided by the size of node, and that way we get you know, all of the necessary nodes. Okay, so let me see how many nodes we have read. So read, maybe we can just go ahead and just print each individual node. Can we actually do that? That's a very good question. So I'm gonna iterate through all of the nodes, right? Maybe by a pointer, because why not? And I'm gonna literally just print their text. It's not gonna look like a string, right? It's gonna be array of bytes, but hopefully we'll see something interesting within this arrays of bytes, right? So this is gonna be the text. And let's just go ahead and run this entire thing. So something failed, undeclared identifier content should have done something like this. And read entire file and declared identifier, because I need to import file. All right, and it looks like it's true, right? So yeah, here are all of the things, and how many of those things we have in here? It should be power of 2, 31, surprisingly. 31. I don't know why, but it is what it is. I would expect actually power 2, but maybe I'm missing something. Anyway, this looks like a correct data, right? So we have some stuff in here, so that's fine. I wonder if is there any facilities in Jai that lets you take C-string and convert it to, you know, to Jai string? Because as far as I know, there's a TMP C-string. Right, so if we take a look at the Jai modules, there is a function TMP C-string which does the opposite thing, which converts the Jai string into C-string, but we want to do an opposite thing. So maybe in the same place where temp C-string is defined, we have a similar thing that does the opposite job. So let's actually go there. So copy in temporary string, copy string, C-string. Ooh, okay. So there is a toString, for instance, right, which allows you to take the pointer to the bytes. You can also take the buffer, but this entire thing kind of two C-strings, allocates memory, C-style strlen. This could be useful, right, because we can do C-style strlen on that thing, and then we can, you know, turn it into a string. So that's what we can do. Yeah, I think that's precisely what we can do. All right, so let's actually implement a function that, you know, prints the tree, right? So print tree. So here we accept the root, which is absolute pointer. We can only pass the absolute pointers. The relative pointers in Jai work exactly like they work in C if you implement them yourself. It's just like Jai automates this entire boilerplate with macros and stuff like that. So basically, one of the important things Jai does is just like automates this and hides this stuff from you. Though you kind of have to be aware of how it encodes, because you may want to rely on that logic. Well, it's not necessarily a good idea, but you know, you have to be aware, right? You have to be aware of that logic, right? Okay, we're gonna have a level, and I program in Jai, and in Jai I do have the default values, so I can do this kind of thing, which is cool, right? Finally, a good language, finally. All right, so I might as well actually open this side by side and start translating this entire logic, right? Okay, so for 0 to level -1, I'm gonna do print 10, like so. Then what I need to do, I need to construct a text, right? So the text is essentially toString, right? Where I take, you know, I can do the following thing using text, text, C-style strlen, and C-style strlen, what does it do? Simple string C-style strlen accepts a pointer to data, so we have to do data, right? And then we do toString. So we do it like that. I wish there was like maybe a better way of doing that. It's a bit cumbersome. TMP, yeah. So you have to do C-style thingy, which is kind of but it is what it is. All right, so then we print this stuff, and now we have to recurse in different places. So we have to do if left, then print tree left level +1. If right, this is right level +1. There we go. So I probably also have to import simple string, but I want the compiler to tell me that. This is not what I want right now. I want to grab anything. Thank you very much. Okay, so cool. Now, what I want to do, I want to print. So I'm going to print tree, node spool, and I'm taking the zeros one and I'm taking the pointer, and let's see if it's going to do the trick. And it does. It works. Right. So the file with relative pointers that we generated in C just works in Jai. So we managed to replicate the encoding of Jai. Right. Unfortunately, you couldn't see that live. All right, you couldn't see that live, but I managed to, how to say that, record that moment offline. That's what I wanted to say. This is actually kind of cool. Right, so yeah. And as you can see, you literally didn't even have to do anything in here. So what's funny is that here I pass a relative pointer as an absolute one, and it automatically converts it to absolute one, because left is a, yeah. And one of the advantages, by the way, the built-in language support provides is that it's type safe. What if I change this thing to int? It's not going to compile. It makes sure that all of the types matched. So this is something that we can't have in C. Of course, you can implement the same encoding in C, but you don't get the same type checking as if you had the built-in support for this kind of thing. So yeah, that's basically relative pointers of Jai, and you can control the size of them, right? So you can provide like maybe 16, and the code, you don't even have to change anything in here, right? So the compiler is going to do everything automatically for you. Or maybe, so, and this is another cool thing. At any point you can say, okay, I'm going to use absolute ones, and the code here, this specific code, is still going to work. Because syntactically it's not distinguishable from the one that works with the relative ones. So it's very ergonomic. It's really easy to refactor from absolute pointers to relative ones and back. So yeah, that's actually pretty cool. So this kind of stuff can be probably implemented with the same level of convenience in C++ if you use templates and operator overloading. Right, so for instance here, what you can do, you can probably define a structure, a relptr, where you would maybe accept as a parameter the storage rather, and the type that you're referring to. So as you can see, the type that we're pointing to is also part of the relative pointer type, so it gives the same benefits of type checking. Right, so the store in here is a storage, right? So, and then you can implement all sorts of operators in here. All right, operator, like this, where you would do all of this decoding and encoding. And the cool thing with C++ approach is that you have a customizable decoding algorithm, right? So the problem with Jai here is that you can only stick to one specific way of decoding things, like decoding relative pointers. It's the way of like setting the height bits with Zor. And if you use a different encoding, well, you have to go back to implementing everything manually. As far as I know, right, maybe there is a way to customize, you know, decoding and encoding of the relative pointers, but I'm not aware of one. If there is, it's actually quite good. I'm really happy. But in C++, you can achieve that very naturally by, you know, just implementing a class like a template class and stuff like that. But at the same time, the advantage of Jai is that since it's a built-in thing, it's a standardized thing. So all of the libraries, if they want to use relative pointers, they use the same relative pointer mechanism, right? So, and in C++, if you want to use relative pointers, like different libraries are probably going to be using different implementations of relative pointers, and yeah, so it is what it is. So the way, by the way, these kind of problems, this kind of standardization between different parts of the application is solved is through the context, right? Maybe in Jai you can come up with a mechanism that adds the decoding encoding algorithm of relative pointers into the context. So if the library is using relative pointers, but you want to supply your own algorithm of decoding and encoding them, you can do that through the context. But maybe it is already implemented like that, but it's just like my random thoughts. All right, so that's basically everything what I wanted to do today, right? So I just wanted to explore relative pointers or Jai in like in a very detailed way, right? And the best way to do that is to actually implement them from scratch in a language that doesn't support them, which is C. And yeah, so that's what we did in here. So that's how they work internally, and we proved that it is in fact true by implementing the cross-parent program in Jai. All right, so I'm gonna concatenate two streams. I'm gonna concatenate the live part and offline part and upload it to YouTube as a single thing. And that's it for the day. Thanks everyone who's watching right now. I really appreciate it. Have a good one, and I see you on the next recreation programming session. Love you all. Mwah.